Hello and welcome back. In this video we're going to look at a particular class of differential equations, in particular a first order differential equation that can be written as y prime equals f of xy. We're going to try to visualize what this kind of equation looks like. Now, of course, not every differential equation can be written in this form, but if you have a differential equation that can be written in this form, then you can visualize it through these things called slope fields or direction fields. So notice that for each xy point on the plane, dy dx equals f of xy, which is what we're looking at here, that's the kind of differential equation we're focusing on, gives us the slope of the tangent line of a solution curve through that point. So think about if you plug in x comma y into the right side of this equation. So x comma y would be plugged into some function on the right side. So that might be like y minus x squared, for example, or y plus sine x. So if you plug the xy pair into the right side of the equation, you're going to get some number. Then dy dx, which is the slope of the tangent line of a solution curve that goes through that point, is going to be equal to that number. So at that point, you're going to know what the slope of the tangent line of the solution curve that goes through that point is. So we can fill the plane with these little tangent stubs. We won't draw the whole tangent line because then it starts to get a little bit out of control, but we're going to just draw a little tiny piece, a little segment of the tangent line to generate what's called, again, a slope field or a direction field. Slope field because each of these little stubs are going to be representing the slope of the tangent line of the curve that goes through that point. Direction field because it also gives you a sense of the direction that the curves are going to be traveling. They're going to be flowing along the tangent lines. So figures 1, 2, and 3 give examples of slope fields. Let's look at figure 1 as a first example. We have y prime equals y minus x squared. So on the right side, this is the function of x and y. This is f of xy on the right side. It's y minus x squared. And on the left side, we've got the y prime, which you could write as dy dx. Now, suppose we just take a point, and I know it's hard to read the scales here. I'll have to update these graphs at some point. Let's take a point like 2, 2. So 2, 2. If we plug that in, we would get, here, let me put it over here. You can tell how prepared I am. 2, 2. So we have y prime equals, and then if we plug in 2 in for y, and then 2 in for x, we get negative 2. So what this is saying is that the slope of the tangent line of the curve that goes through the point 2, 2 is negative 2. And then if we look over here at 2, 2, again, I know it's a little hard to read, but here's 2 and here's 2. You can see this tangent line has a negative slope, and it's supposed to be a slope of negative 2. It's, again, a little bit hard to tell, also because the y scale is a little different from the x scale, but that's supposed to have slope negative 2 right there, that tangent line. So if there was a little piece of the curve, it would be going something like that, along with the tangent line, same direction as the tangent line. Now you could use the other tangent stubs to help figure out what the flow of that curve is as you're moving around, as you're going from across from left to right or whatnot. So it kind of flows along with these other direction fields. It's going to be going steeper and steeper down as you go to the right. As you go to the left, if you're going kind of backwards, I know these things have arrows, but they can go both directions. You might have something like this. You're following along with some kind of the direction of those tangent curves. So it might be something like that. It's hard to know exactly what it looks like, but something that flows along with the tangent stubs. So whatever the equation for that graph is, that would be a solution to our differential equation. And in particular, it would be a solution that goes through the point 2, 2. So 2, 2 is like your initial condition, like we talked about in the previous video. This would be y of 2 equals 2. That's an initial condition. Now it doesn't happen at t equals 0, but any point on the plane would be considered an initial condition. It's the extra bit of information you need to pull out a particular solution from all the rest of the solutions. So figure 2 is y prime equals y plus sine x. So here you can kind of see that there's the sine x is affecting the slopes of the tangent lines in a sinusoidal kind of way. You can see the sine curve a little bit there. Now it doesn't mean that the solutions will necessarily be sine functions, but it's definitely affecting the slope fields in that way. All right, and then figure 3, we have y prime equals y plus sine x, the same differential equation as figure 2. But here we're putting in some initial conditions, like -4 comma 0 looks like the initial condition for the first curve. And that one looks like rises a little bit as you go to the right, and then rises more steeply as it gets caught in the current of the direction field. Now it's amazing because if you just veer off a little bit and do, instead of -4 comma 0, you put -4 comma, I don't know what that is exactly, maybe like negative a third. That makes for a totally different solution. It goes up, doesn't quite make it above the x-axis, and then veers down. So small changes in your initial condition can affect huge changes in terms of the function that satisfies that initial condition, the particular solution or the particular function that satisfies that initial condition. These are just some more examples in figure 3 of how the solution curves are flowing with the tangent stubs. Now, in example 3, we're given a differential equation y prime equals negative y to the fourth. And it's asking, without making a slope field, what can you say about the given solutions of y prime equals negative y to the fourth? And I'd like you to pause and just think about that. So pause the video and think about that for just a moment. See if you can think about what kinds of features this slope field would have. And then when you come back, we'll take a look together. So welcome back. So one of the things is that it doesn't matter what initial condition you plug into this differential equation. You're going to take whatever that number is, raise it to the fourth power, which will be a positive number, and then multiply it by -1, which will be a negative number. So the slopes of the tangent lines are always going to be negative for this differential equation. They're always going to be going down as you go to the right. So that's one of the first things we can mention. So the slopes of the tangent lines, or you can say the solution curves, slopes of the solution curves, just for short. Slopes of the solution curves just means the slopes of those tangent lines. They're going to be negative, and so they're going to be going down as you go to the right, in other words, decreasing. Another thing to notice is that all of the examples in figures 1 through 3, I guess it was really only 2 examples because figure 2 and 3 were the same, but in those examples we had both y's and x's on the right side of the differential equation. But in this one we only have a y. So how does that change or how does that affect your slope field? Well, it means that it doesn't matter what x value you're at, the slope of the tangent line will be the same. So if you pick a particular y value, then it doesn't matter what x value you're at, the slopes are always going to be the same. So though, like for example, if you plug in y equals 1, you'll get a slope of -1. So that means all along the horizontal line y equals 1, your slopes are going to be -1, all along that line, no matter what the x value is. So you have the same slope for a given y value regardless of the x value. Equations like this are sometimes called autonomous equations, and you'll take a look at them in one of your computer labs. So that's it for this video. Thanks for watching, and see you in the next one.